Hello. In this segment, we're going to talk about instruction set architectures. Up to this point, we've only examined the little man computer, which is a one-address machine, also known as an accumulator-based machine. But that's not the only kind of instruction format that we can have. The instruction format determines the number of addresses that we will use. As I mentioned, a one-address machine such as the little man computer uses an accumulator. Why is it called a one-address machine? If you look at each instruction, there is only one additional operand that's specified. And yet, if I carry out an add, I have to add at least two things together and then do something with the result. So there's really three operands that I need to have, the two sources and the one destination. In an accumulator-based machine, we only get to specify one. One of the other sources and the destination is the accumulator register, and so we can specify only one memory address for performing the add. However, we can also talk about zero-address machines in which we specify none of the operands. They're all implicit. One-address machines that we've seen, such as the accumulator, and two-address and three-address machines where everything is explicitly given. Let's take a look at a zero-address machine. In a zero-address machine, also known as a stack-based machine, all of the operands are implicit. All operands come from the stack and all results go back to the stack. So if we, for example, are trying to calculate the result of this expression on a zero-address machine, we could have code like the following. I push A onto the stack, which takes one memory reference. I have to go out to memory and fetch the A, and then I put it onto the stack. If we execute that, we would see the stack grow by one element. I could then push B onto the stack. Again, that goes out to memory and pulls B from memory and pushes it onto the stack. So now both A and B are on the stack. I then run into the multiply instruction. The multiply instruction needs two things to multiply together. So where does it get those from? From the stack. Where does it put the result? Back onto the stack. So it pops A and B off the stack, multiplies them together, and pushes the result back onto the stack. Now we push C onto the stack, and D, and E onto the stack. And then we need to do a multiply. So we're going to pop E and D off the stack, multiply them together, and push the product back on. Then we're going to do a subtraction. What are we going to subtract? We're going to subtract D times E from C, and then push the result back onto the stack again. Finally, we're going to do an add. What are we going to add? The two things that are on the top of the stack. And so we end up with our final computation on the top of the stack. What are we to do with that? Store it into the memory address indicated by A using a pop instruction. Now, in a stack-based machine, the stack is a set of very fast registers, which minimizes the number of times we have to go to memory. And so we only have to go to memory for each operand that we're pulling from memory. So if we sum up the total number of memory references that we have, we find 6 memory references in this code, not including the instruction fetch itself. Now, there are a number of instructions here, and we would have to include that in our final calculation, as we'll see later. A one-address machine, as mentioned previously, is an accumulator-based machine. The accumulator is one of the sources, and it's also the destination for where the operation goes. So, if we rewrite this expression using the accumulator-based assembly language, we would load A, multiply it times B, and the result A times B would go into the accumulator. We can then add C, and that result would go into the accumulator. We then are completing a temporary instruction or a temporary sub-expression, and we have to store that back into memory at T1. We can then load D, multiply by E, and store that back into T2. So now I have a T1 and a T2 sub-expression. I have to subtract T2 from T1. So I load T1, I subtract T2, and store the result back at A. There are 10 memory references because each of these things refer to at least one memory address in each instruction, not including the instruction fetch. In a two-address machine, we find the two source operands in the instruction, and the first one is also the destination. So, if we rewrite that code again, we find the following. We move A into T1. This makes a copy of A in a temporary variable. I can then multiply that temporary variable by B and store the result back in the temporary, add C to the temporary and store it back in the temporary. Now I have completed one of the sub-expressions. I then have to make a new temporary variable, T2, that is a copy of D. I have to multiply that temporary times E, and now I want to do a subtraction of the two temporaries, and the result will go back into T1. Finally, I can move T1 into A, completing the store. Now, if we look at this, there are a lot of memory references, 18, not including instruction fetch. But if you'll notice, we've reduced the number of total instructions. Now, the question arises, what if T1 and T2, instead of being memory addresses, what if they were registers? If I replace T1 and T2 with R1 and R2, indicating registers that are temporaries, now it cuts the memory references back down to 6. This is called a 1.5 address machine. In a 1.5 address machine, one of the destinations is always a register. In a 3 address machine, we're going to explicitly specify all 3 operands, both sources and the destination, with the destination coming first. Again, rewriting that expression that we saw earlier, this becomes very simple. Only 4 instructions. Take A and B from memory, multiply them together, and store the result at T1. Take T1 and add that to C, and store the result back in T1. Now I've completed a half of a sub-expression. Take D and E, multiply them together, and store the result at T2, and then take T1 and subtract T2 from it, and store the result in A. Now, the number of memory references here is 12, not including instruction fetch. But now we've only got 4 instructions that we need to fetch. What if T1 and T2 were registers instead of memory locations? Now we're back down to our 6 memory accesses and only 4 instructions. But those 4 instructions, because they specify 3 operands, are going to be much longer instructions than the push or the pop of a 0 address machine. So let's compare these 4 architectures on that little simple program for calculating those expressions. Let's assume that our architecture has 8 registers, 32 opcodes in 5 bits, 15-bit addresses, and 16-bit integers. So this kind of determines how big an instruction is and how much memory we're going to move around. Which instruction set architecture accesses memory the least? If we add them all up and we look at the 0 address, the 1 address accumulator, the 1.5 address machine, 2, 3, and the 3 address with registers machine, it turns out that there are 2 very clear winners. The 1.5 address machine, where one of the source and the destination is always a register, has 257 bits total moved back and forth to memory. The 3 address machine is also a winner at 248 bits, where we use registers as some of the intermediaries. So the 1.5 address machine is a very RISC type machine, a reduced instruction set computer, and the 3 address machine is a very CISC based machine, a complex instruction set. In summary, the instruction set architecture determines the format of instructions and thereby the assembly language that we will be writing in. The 4 basic types of instruction set architectures are 0 address, that is stack-based, 1 address, that is accumulator-based, 2 address, and a variant that includes registers that's a 1.5 address machine, and then 3 address and a variant where we also have registers for temporary variables. And the instruction set architecture dramatically affects the number of times memory is accessed, which, according to our von Neumann bottleneck, is something we want to minimize.